Good morning.
Hey, good morning, Dr. Forte.
I was not sure if my technology was working.
Morning.
Good morning. Yeah, I'm doing from home. There may be some noise in the background. Looks like they're doing some repair works.
That's fine.
Okay. Yeah, so how was the week so far?
Yeah, it's all right.
Okay.
It's all good.
Okay. Yeah. I think Saurabh said he's going to be in flying this morning, so he won't be able to make it in the tutorial. So I thought we should just as well start at 10 o'clock and then take it from there. I've looked at the what we wanted to cover the last week. The last week was actually supposed to be today, but we missed the first week. And I think it's very different from what we've been doing. And I'm not too sure you're going to get much out of it. So I just thought we should just focus on finishing confirmatory factor analysis. And then if we have some time left at the end, we'll just go through what we've done and how it all comes together. So the latent class that I put at the end is conceptually different from the latent classes that we have been doing here. And I'm not too sure it's going to add value doing it in one lecture to you. So I thought let's just focus on confirmatory factor analysis and then take it backwards to principal component analysis, factor analysis, structural equation modeling, and confirmatory factor analysis.
Okay, that means next week will be last lecture or today?
Technically, we can make today last lecture, and then you have tutorial when Saurabh comes in whatever else you want to have clarification on. So you only then have tutorial afterwards. But if after today you feel that you want to use next week to put everything together, then we can have a lecture. If you don't feel so, they can just have a tutorial.
Okay.
Yeah. So it will be entirely up to you what you think. Whether you think that you have a package in front of you that you can use for your work in terms of the course.
What about the assignments?
I've already posted it. I think I posted the assignment, was it yesterday or Tuesday? I think it was on Tuesday. So, okay. So what I think I just realized you left before I discussed the end. I suggested that I forgot to send you an email that instead of doing one assignment, then the comprehensive, I just do you the comprehensive. I think I put that when I post the assignment, I put a notice on that because basically what the second assignment was going to do was take structural equation modeling and confirmatory factor analysis. Then the comprehensive will just take everything together. And I thought instead of going to that, and normally the risk is that if the continuous assessment is not well done, then one will balance the other. But I think the first one was okay. So I just decided to put comprehensive where the first part has a smaller amount from principal component and factor analysis, and the second part was weighted towards this one that we've not yet done. So if you look at the comprehensive, about 60% comes from structural equation modeling and confirmatory factor analysis, and the 40% comes from what you've already done in terms of principal components and the factor analysis. So I think that should balance up the need to do one more piece of work. So just check again. I posted that on, maybe it was yesterday. Yeah, you saw it.
Yeah.
Okay. So I hope that's fine. Again, I have not overloaded it. One of the things I found at Western is that sometimes they use quizzes. I tried to use quiz. I wasn't sure. I didn't think that I could really test what we were doing through quizzes, because one of the ways was to give a quiz in between. I tried that with the first couple of courses that I did, and I chatted with the students, and I wasn't sure that maybe I was not setting the questions as good as it could be, but I've discussed with other colleagues what extent can you use quizzes to assess a graduate student. I wasn't sure, so I just didn't bother with quizzes. Yeah. Okay, so today, the example you gave was so good. I wish you had looked at that at the beginning. I've been looking for examples of doing confirmatory, but maybe we'll talk about that in the course of this. It was so good using it to look at what structural equation modeling does. And my mind is that if you're okay with it, then we can also even use it to see how you can do some data and include some of the factors as latent variables and see how it looks like. And also, I'm talking about the example you sent by email.
Yes, you can, yes.
Okay, because it really brings up the issue of sample size problems when it comes to model fitting. You see that very clearly the moment you start changing the nature of the data, which we are going to discuss here anyway. But I just thought I would do short notes, and then most of the thing that we're going to do today is going to be practical work.
Okay.
Yeah, so I try to put some learning outcome just to focus us what we should be looking for. And the idea is that we want to learn what is confirmation factor analysis and how it differs from exploratory factor analysis. And I put exploratory in quotes because usually when we talk about factor analysis, we mean what we call exploratory factor analysis. Okay, so when we say factor analysis, we don't put exploratory, but that would normally mean exploratory factor analysis. It's only when we go to confirmatory that we put the adjective. So one of the things about factor analysis are this idea of the measures used to evaluate goodness of fit. And the reason why you need to evaluate goodness of fit is that confirmatory factor analysis is conceptually a hypothesized relationship. So if I say data are normally distributed, the only way I can check whether it's true or not is to have a measure that I can use to say if it is normally distributed, this is what should happen. So the same thing comes here. When we say confirmatory factor analysis, we have a factor structure that we've assumed, and then those measures are used to evaluate whether the factor structure is correct or not. So one of the things we are going to do is to specify and fit the model. And I think this is sometimes one of the challenging aspects when you define what you want, how to write it into a conceptual model. When I look at what a lot of people have done in literature is that you start by sketching what you want in a graph, in a path diagram, for example, and then you try to translate that into your model, whatever software you are using. And sometimes sketching may not necessarily be easy, but the most important thing is that whatever model we have, whether it's written in words or is written as a diagram, can we translate that into a model and then use a statistical package to feed it? Okay, so that will probably dominate most of what we've discussed. Then, of course, instead of one of the things that you look at is that if you are using measures of goodness of feed, but you need to also be sure that the diagram is what you were intending to the relationship that you were intending to do are correct. So if you specify a model, it's a good idea to see whether that model produces the path diagram that you were hoping for, that you were looking for. Of course, there are many ways of writing a path diagram, which is sometimes can be a challenge in order to interpret it, but we should be able to obtain the path diagram. And there's this idea of standardized and unstandardized coefficients, which I find in literature. I forgot to record that. Let me go, just in case we may want to.
It's recording.
It records automatically. Eh? Okay, because it's teaching Zoom. So all that empty space will be there that I put on and I didn't realize it was recording. Isn't it? Normally, we have to ask your opinion. Should I record? You say yes, but it looks like this one doesn't bother that. Okay, yeah. So as I said, the sample size limitations are really a challenge, and I've just touched on that. Normally, in most statistics, we talk about sample size, but it's almost obvious. But what I find is that in structural equation modeling and in confirmatory factor analysis, the number of parameters are not just the path coefficients. You also have the variances and covariances of various variables in, because the moment you are using some variables as what you call endogenous, which means the endogenous variable, remember, serves both as a predictor and as an outcome within the same model. So once you are including those ones, the variances, covariances becomes parameters themselves. Whereas when you're doing just a normal regression, when we talk about the number of parameters, we're just talking about the number of predictors in the model plus the error. And then your sample size, your error degrees of freedom is just your sample size minus those number of parameters. Now, when we come to confirmatory factor analysis and structural equation modeling, it's a whole different concept. The variances, covariances can also become parameters, and they add up to the number of parameters in your model. So you can suddenly find a model that looks very good, doesn't fit, and you don't know why it's happening. But the problem with sometimes it's not just the model specification, is that the sample sizes are inadequate to do the estimation. Yeah. So now the next thing that I want to do is we ought to obtain and interpret the goodness of fit measures. Although I didn't spend too much time on this, mainly because, but we'll do something on it, mainly because the goodness of fit mostly ad hoc. But and that's learn a range of default and additional parameters that you can get from your package. So that's more or less what I hope we shall achieve by the end of this session. Yeah. As I go along, please, if you have any questions, just ask. Since we are not in a classroom face-to-face situation, you just ask your question. Don't bother putting up your hand or anything. Just stop me and ask a question if you want to.
Okay.
Yeah, because sometimes you put out your hand, I may not see. Then you say, yeah, my hand is up. The way my screen is, I may not see the hand up. So just get in and chat, and I will stop.
Okay. Hi. Sorry. Just a quick question.
Mm-hmm.
So this is the learning outcome for this week.
Yeah.
So next week. So ideally, there's no lecture. And are you trying to put a confirmative
Analysis. Confirmatory. Mm-hmm.
and latent analysis all together in this week?
No, I'm saying that the latent class analysis that we're doing is a conceptually very different topic. It doesn't really fit into any of what we've done so far.
Okay. Yeah.
Yeah. So my thought was let's just leave it out.
Okay.
Yeah. The reasoning, as I said, I will actually, if we have about 10 minutes at the end, I will give you an indication what it's doing, so you appreciate it. And also, even the software for fitting latent class analysis is very different. And I only know this an R software. I don't know any software in any other platform that they use for that.
I see.
Yeah. So yeah. So that's why I said that my thinking is that we should just leave it out. And yeah.
And so next week will be like a final tutorial for everything.
Exactly.
Okay, got it.
Yeah.
Thank you. Yeah.
Oh, you're welcome. Yeah. So here I said let's just again recap what we've been doing in terms of factor analysis. And the idea is that factor analysis data, we have data on a set of correlated variables. Okay, or data on a set of correlated variables are available. So the most important thing in principal components factor analysis is that we have correlated variables. And those correlated variables are measuring something. They have something in common that creates the variability among them. In factor analysis, we're interested in the correlation structures. So if there's correlation structure is just one structure, then we expect one factor. If the correlation structure indicates two groups of variables, we expect two factors. If the correlation structure implies or seems to suggest three groups of variables, we get three factors. So that's basically what we've done in factor analysis. So it is believed that the correlation structure among the variables are due at least in part to some underlying cause or causes. And those underlying causes we call latent factors. So those are the assumptions we've done in factor analysis, which underlies confirmatory factor analysis. So for ease of modeling, if there are more than one potential causes, then these are assumed to affect the measured variables independently. So what we're saying is that we want underlying causes which themselves are independent of each other. If they are themselves correlated, it doesn't help the mathematics of evaluating. So that's why we made the assumptions of they factor themselves being independent. So the idea is that if you are looking at the size and shape of a person or of a tree are independent of each other, for example, and then they can affect how tall the tree goes. Well, I don't know. I think that's a bad example. But the size and shape of a person define the person from independent dimensions. So the effect of each latent factor varies with each measured variable. So that would call here the factor loading. So if I just say factor 1, the model is specified by one factor and I have x1, x2, x3, then the coefficient of x1, x2, x3 will vary. If I have two factors, the coefficient of x1, x2 will vary within factor 1 and within factor 2. So that is what we call the factor loading. This is just a review of what we did before. The extent to which the factor solution explains variability in each variable varies from one variable to another. Okay, so the amount of variance that a factor explains, or the factor solution, sorry. You remember here I'm saying the factor solution. So when we have said a factor solution, if our model says one factor is enough, then the factor solution will be that single factor. If our model says we need two factors, like you remember the cutoff when we use the scree diagram, if from our scree diagram we say we are keeping two factors, then it's a two-factor solution. Okay, so I hope that is clear. If our model says we keep three factors, then that's a three-factor solution. When we take that factor solution, we can compute our communality, which will be the proportion of variance in each variable that is explained by the factor solution. Okay, so we are saying that that itself differs from one variable to the other. And by extension, the specific variance also differs because the sum of those two will give us the total variance in that variable. And because our variables are always standardized to have unit variance, it means the sum of the specific and the communality should give us 1 for each variable. Okay, so these two statements are basically complementary in the sense that the truth here and when this is true, this will also be true. Okay, and if you've done any form of regression, which is what we are really doing in structural equation modeling, what we are basically saying is that when we take the total variance in a variable, we can partition it by the variance that is explained by the model and the variance that is unexplained, or the residual variance. Okay, so this is like partitioning the variance in a variable, in our outcome variable, into the variance that is explained by the model and the variance that is not explained by the model, which we normally call residual variance. Okay, so the original correlation matrix can be partitioned into the part due to the communality and the part due to the unexplained specific variances. We didn't actually, okay, I think we wrote a bit, but we didn't really go in. We wrote a little bit of mathematics, but I've stayed away from math since then. But the basic point is that once we divide our factor model into the common part and the random part, the same thing will now go into our correlation matrix. And because the factors themselves are done to be, our factor solutions are done to be uncorrelated, that means what is really being affected are the diagonal entries in the covariance matrix. Okay, the diagonal entries are what is being affected, and that can create some problem themselves because the mathematics of correlation matrix says that it must be positive definite, which means that the covariance cannot be larger than the product of the standard deviations. Okay, in which case now the correlation cannot be bigger than 1. That's another way of saying it when you standardize. So if now you've partitioned the diagonal entries into the communality and the specific variance, then if you write this partition, you could lead to a situation where one of the matrices does not satisfy the correlation matrix. Okay, so that is a problem. We didn't actually go into that, but it sometimes happens. And that can also create problems within your confirmatory factor analysis that your model may not fit. So I'm just talking, I just thought you just give us a brief of what we've done. If there are any questions before we jump, if there's something that you want to revise in the factor analysis based on this, then you can just ask before I go ahead. We're okay?
I'm good, yeah.
Okay. So let's now go here. So what is confirmatory factor analysis? So in the confirmatory factor analysis, a factor solution has been determined for a given set of correlated variables using available data, okay? So that's basically what is happening. So we've done our factor analysis based on some data, and we've determined that the data may be divided into two factors. Factor one comprised of this set of variables, factor two comprised of this set of variables. So that is what our confirmatory factor analysis now is to use a new data set, maybe arising from a different population, and interest is to evaluate if the known factor solution is still valid. Okay. So that is basically what our confirmatory factor analysis is doing, which is great because we just say confirm, and we are confirming the factor structure. So we wish to use new data on the same set of variables to confirm a previously determined factor solution. In other words, can the assumed factor structure be replicated using the new data? Okay. So I said this is hence a type of goodness of fit solution. So if you look at that, the measures of evaluation are basically all goodness of fit measures. They are just different forms of goodness of fit. Of course, the most standard goodness of fit measure is the Pearson chi-squared. The Pearson chi-squared says this is the observed structure, this is the expected structure, and then it takes the difference between those two, standardize it, and then relate it to a chi-squared. So that tends to be the best goodness of fit measure. But things like residual mean squares are used in regression for goodness of fit as well, which is just taking the residuals and finding their variance, and then using the statistics to test for the significance of that variance. Okay. So that is basically what it is. So what it means is that once we've done factor analysis, the only thing we are doing in confirmatory factor analysis is evaluating the goodness of fit. That's basically what we're saying. Specify the model that we think and then evaluate it. And what I think we'll do in the practice as well is that what if you find that your model does not fit? What a lot of researchers then do is to go back and do exploratory factor analysis to say, okay, if my model does not fit, what is the factor solution to my data? Okay, what solution best fit my data? So I'll go back and do my exploratory factor analysis and say, oh, okay, these are the factors, and this is how it differs from the proposed factor analysis. And that's a good thing to do if you're doing confirmatory factor analysis. Once you do your analysis, if your factor structure has not been confirmed, then you can go back and do exploratory factor analysis, what you may call unsupervised learning in data science, because exploratory factor analysis is what you call unsupervised. The model tells you what the factors are, or the data tells you what the factors are, sorry. Okay. So in here, I just took a whole list of what I see in the literature on those measures. There are so many of them. And the ones that seem to be reported as the most common are this root mean square error of approximation. And the recommendation is that a good fit, the value should be less than 0.5 for a good fit. And then between 0.5 and 0.1, the values are some marginal fit and so on. You can put some adjective to define, but it's still an acceptable fit. But when the value is greater than 0.1, it's normally considered as a poor fit. So that is one of the standard interpretation. And this looks very much like our p-value. A p-value of less than 0.05 means that we reject H naught. Whatever our null hypothesis is, we reject it. A p-value between 0.05 and 0.1, whatever our null hypothesis, if we say that, okay, there's some moderate evidence against it. And when p-value is greater than 0.1, we say there's no evidence against the null hypothesis. So if you look at the root mean square error of approximation, the interpreting is very similar to what we do with our p-value in hypothesis testing. Okay. Yeah.
I have a question here. I've read other literature and other books. The value is different from these resources. Like there's some people say no more like
Yeah, 0.6, yeah.
no more than 0.8. It considered a good fit or acceptable fit.
0.08 or 0.8.
Is this a very restricted value, or is it something this is something different from discipline to discipline or from measure to measure? Like, for example, could be different in nursing or in medicine.
Not really. The biggest challenge, I think I say it in here. Like one of the literature says, one guy did a lot of study on categorical data and he recommended 0.06 here. I think it's one of the literature that I've shared with you. He recommends from 0.06. These are what I call ad hoc measures. I think I've probably said it down here. I will talk about it there. These are really what we call ad hoc measure in the sense that we don't have we can't derive this from calculus. Okay, in statistics, measure that we say this is true. Like if I say this is a normal distribution, I have a probability density function for a normal distribution. I have the parameters. I can generate data and show that this is normal. These ones are mostly ad hoc measures. So I wouldn't say it's. I don't think it's not based on the field of study. It's based on what people have proposed.
Okay.
Yeah, but did you say 0.08 or 0.8? Because that's very different. This one
0.08.
That's correct. Yeah, that's correct. Because like I said, the 0.08, you see this value here. You see this one say 0.05 and this one say 0.1. Between 0.08, 0.05 and 0.1, there are other qualitative statements being used.
Okay.
Okay. So, but substantively, one of the literature that I shared here did a lot of studies using categorical data, and he suggested that this should be 0.6. Okay. But between 0.05 and 0.1, they don't consider the profit. So if somebody can go there and say, okay, use 0.08 or use point this. But you see, the challenge is not only there. You know where your challenge is? Your challenge, okay, I'll go there and just talk about it when we finish this one. You'll see where the challenges are.
Okay.
Yeah. So you have this comparative fit. I found that these three, as you have read, probably are the most popular ones being reported and used, maybe because of their history and so on. And yeah, maybe because their history could also be area-wise. And some people use this idea of going back to reliability. You know, reliabilities tend to be Cronberg alpha when they are looking at reliability. So some people like coming from reliability perspective, go back and look at the issue of reliability, and so on. And this one, I found this one very interesting. The average variance extracted. Well, what they are going back is to say, okay, if this is my factor solution, how much variance is being explained by my factor solution? Almost like somebody thinking like our proportion of variance explained, but in a matrix form. Okay, so there are so many measures. But as I said, just like the question you asked, the issue comes here that unfortunately the measures of feed, especially their cutoffs, are not based on analysis, are not based on strong statistical theory. Okay, so we cannot use calculus. Like calculus, we say I want to find the maxima and the minima. We can't use that to tell us that these are objective cutoff points. So it's more or less from resampling, sampling, and resampling, which means often they will yield conflicting conclusions. Although maybe I'm being unfair, it's not only this measure that yield conflicting conclusions. Even when you do simple regression and you do variable selection, each variable selection method that you use can lead you to arrive at a different conclusion. So it's not only for this, but what you will find a lot of time is that if your data are not like nice data, like the one that will simulate and fit your structure, one measure may be saying no, it's a good fit, another measure may be saying it's not a good fit. So it's even the most popular measures, such as the root mean square error of approximation, comparative fit index, and Tucker-Lewis index, rely on normally distributed continuous data and maximum likelihood estimation. And this is a big deal because most of the data that I've seen being used in factor analysis, confirmatory factor analysis, are nowhere close to being normal. To start with, the scale of measurement in a lot of time is ordinal, but it's just been treated as ratio scale, which means it cannot be normal. But even when the scale of measurement is continuous, the assumption of normality is a bit stretching a bit far. So if the data were purely normally distributed, this would be pretty good measures. Okay, they will be very good measures. They will do a very good job in giving us a summary. But when they are not normal, there are other methods of fit apart from maximum likelihood, of course, which we use when the data are categorical. But even within that context, lack of normality will also affect the extent to which these measures are giving you a very good thing. So if you are very convinced about your factor structure and you think that more or less explains, the data explain what you were expecting, you may just have to go along with the results. And know that every result that you have has limitations. And therefore, don't be surprised if you don't get the results you were expecting. I think that is the summary in which I would say. The reason being that the studies that did that study, the studies that reported what you were expecting could not be replicated in general because of these failures of assumptions. Okay. Well, we always assume that a study showed that this variable was a particular variable explain another variable very well based on this measure of test. But then if that study cannot be replicated because the measure itself depended on the data and the assumptions, then you may find that your study does not give the results you were expecting. I think that's what I'm saying there. So you shouldn't be too worried unless the model really just failed. But if some of your measures here are telling that it's a good fit and some are saying that it's not that good, then maybe you just make a subjective decision, even though we don't like unduly subjective decision in statistics, but you make a subjective decision. One other thing, maybe go ahead first.
Go ahead.
Yeah, one other thing that you'll find, and you'll find because this data that I have is simulated, is that sometimes you get the perfect measure. Like you tell you that this one is 0 and this one is 1. Usually when that happens, the first thing that, for a normal statistics, if I see an residual mean square of 0, it tells me that I use up all my degrees of freedom. That means the sample size was just large enough to fit the model. Then my residual mean square will be 0. So it's like if I see a variance of 0, I know that there was no variability. Okay, so if I give you data set and you told me that the variance was 0, the standard deviation was 0, I know there was no variability. Everything was a constant. Now, if I take 2 points and I fit a line to it, that line will also be a perfect fit. Because for 2 points only, you'll get the perfect fit. If I take 3 points and I want to explain by 2 variables, I'll get a perfect fit. So that's what I mean by getting an RM mean square of 0. So when it's this 0 or very close to 0, it may not necessarily be how great the fit it is, especially if this is 0. If root mean square is 0 and this one is 1, then it may tell you that you more or less, your sample set was just good enough to fit the data. Okay, that's why maybe say may not be telling you that your model is excellent. So that is a warning that you should have, that yes, good fit means that this is very close to 0, but very close to 0 should also make you go and look at your data and say, my parameters, my sample size, are they too close for comfort? Okay, you want to ask a question?
Yeah, I have 2 questions here now.
Sure.
First, like which one of these good fits criteria is important to decide, to make me to decide if either the model is good fit or not?
That's why I said that these 3 are the most popular. So my suggestion would be that you use these 3 as your starting point and only look at anything else when you are not very sure. If, for example, these 3 are giving you something that is conflicting, maybe you can look at the others.
Okay.
Yeah.
So
yeah.
The other question is, now what you're saying, what I understand is that even if I have the root mean square and TI and CFI in a normal range, that doesn't mean that the model is in a good fit. Is it right?
No, if it's normal range, that is good. There's nothing to worry about. If the value becomes like really at the end, the like best fit, like 0 here and 1 here. You see, if you get this one 0, this one 1, this one 1, this is more, you see a cutoff say greater than 0.9. So greater than 0.9, so I see 1 here, I say, wow, this is great. Less than 0.05, I see 0, I say, this is great. When you have those extremes, the suggestion is that go and check to see if your it's not the matter of fitting a straight line to 2 points. You see what I'm saying? Because if I fit a straight line to 2 points, there was no error. You see a point. There can only be one straight line to joining 2 points, so there's no error. So as I get results of 0, I say, wow, what a perfect fit. But then, oh, it's only because there were only 2 points. If I put a third point, can my residual still remain 0? If I put 5 points, can I still get a residual of 0? Because that will tell me whether it's a good fit or not. But in the multidimensional space, we don't see that that is 2 points. What we see, what the 2 points correspond to saying, I have 10 parameters and I have 11, a sample size of 11. Then that is equivalent to fitting a straight line to 2 points in a 10-dimensional space. You get that? If I have 10 parameters and my n is 11, that's equivalent to fitting a straight line to 2 points. You'll get the perfect fit, but it doesn't mean that the relationship is perfect. If I get 9 parameters and I get a sample size of 100, I will get a perfect fit. You get that? I'll get perfect fit because my number of parameters and my sample size are my sample size minus 1 are basically the same. Now, sometimes it may not be sample size minus 1. We may be subtracting some other factor depending on how the variables contribute to the degrees of freedom. So that's all we are cautioning here, that if you get this one, sometimes if you get the manuscript with those extreme values, not just in because I've not sent manuscript on confirmatory factor analysis, but in areas of statistics, when you get perfect feeds, most reviewers who know what they are doing will be suspicious of the data. Okay, because real life is never really expected to be perfect. Occasionally it is perfect. If I go and win a lottery of 70 million, I will stop worrying about money. I can do any work I do, but I need a lottery, so that doesn't come often. So when you get a perfect fit, they say, no, it's like winning a lottery. Was it a lottery or something else? So they go back and check the data. Go and check, was there something in your model that is causing that fit? Okay.
Yeah, but and then what should I do? Like, for example, in my measurement model, one of the variable, the fitness result gives me like root square 0 0, like 0, and the CFI and TI was 1.
So that's why I'm saying that in that situation, just check your data again. We'll go down and see some, and we can look at some of the things that you can check. Because if you are comfortable that your sample size and parameter space are very different, then it's okay. You see what I'm saying? Like if I know that my sample size was 10 and I fitted a straight line and I get an R squared of 0, root mean square of 0, then I know it's a perfect fit. There's no question, because the thing that can cause it, the sample size was large enough to say that if it is 0, it is 0. Okay. So I always start worrying. See, our worry is coming because we're in the multidimensional space that we cannot visualize. So we cannot visualize the multidimensional space, we start being suspicious. But if we can visualize, if we can see what is happening in IE, I know that I have a sample size of 300 and the model that I'm fitting has 20 parameters. I don't need to worry about that. I know that is a good fit or it's a perfect fit.
Yeah. And I think because it's only in this model. I tested the other model with the same
data
variable and gives me different with the same sample size and gives me different results. So
you're happy with the result. So you should be happy with that result, because you think that the problem is not overfitting. In fact, that's what constants. So overfitting means I'm using very little data to fit with too many parameters. So
yeah, I don't think it's a problem. Yeah, that's I feel
comfortable with it.
Yes,
which is what you want in the first place. You remember, that's what we want. The only thing is that once you see it, don't just celebrate. Go and check to see, is there a problem? Is there some issue here that I'm overlooking? Once you are satisfied with that, that is actually what you want in your model.
Okay.
Yeah. So here, I think I already talked about those limitations. And this reference I've just put, I think they're also in the notes. But I think they do some good discussion. So this example, I found it really interesting because it had a lot of, this is based on it. It has a lot of data. I tried to look for the source of data. I couldn't see it, so I just decided to generate it. Okay, I just decided to simulate it. I didn't put any noise on it, which I should have. Putting noise means that the way we simulate it, anyway, simulated data should have some noise, but sometimes I also add some noise component to it. So I didn't put any noise, but this is basically what they had. Unfortunately, my plotting packages could not produce this sort of shape. This is what is in the paper, okay? The paper by this. And you say this study is actually based on ancient Chinese and Korean medicine, which has been there for a very long time. And they seem to have come out with factor analysis. This is just one component of that, of the medicine or whatever. So they come out with this, and they have a 25 items questionnaire, which they believe that you can read the article. The article is there. It's quite interesting. So this is a big model of 25 items, and here we call it a 6-factor solution because we have 6 latent variables. So we call this a 6-factor solution, and this is how the different items are weighted on each of the factors. Okay, and what is interesting with this one is that all of the variables here are on, I think there are 7. Each of the 25 items is rated on the 7-point Likert scale, and this is how they are rated. So 1 is disagree very strongly. Okay, I think this command should not be there. So this is disagree very strongly. 2 is disagree strongly. 3 just disagree. Very interesting, this comment. I've always asked my colleagues in the social sciences, what do you mean by neither agree nor disagree? But so 4 is neither, they say standing on the fence. 5 is agree, 6 is strongly agree, and 7. So this is the scale that they have used, okay, in order to come up with these factors. Now, remember something we said about normality? Obviously, data on this scale can never be normal, isn't it? This can never be a normal scale. First of all, they are discrete. Secondly, the range of value is very small. So we know that can never really be normal, but we are assuming normality. There are areas where the normal distribution approximates a lot of distributions under certain conditions. The very first of those conditions is if you have very large sample sizes. Okay, so you have very large sample sizes, almost every distribution can, well, not every symmetric distribution will look normal. What do you mean by symmetric? If this K is such that the majority of people are around here, neither agree nor disagree, and the proportion of people falls becomes lower and lower to the left and higher and lower to the right by the same magnitude, then this data for a large sample set will look very normal. So the normal theory assumption will hold. Okay, it's the same as saying if I have a binomial distribution where P is 0.5, probability of success is 0.5. Then with a large number of people, the binomial distribution will look, when you look at it, you will not distinguish from a normal distribution. Okay, it will look exactly like normal because the probability to the left of the mean are the same like the probability to the right of the mean for the same space. So in as much as we've said that this is not normal, the normal distribution can be used to approximate a lot of distribution. Even the Poisson distribution, which is very asymmetric, for certain value of the parameters, the Poisson distribution, the normal distribution can be used. So in as much as I said this is not normal, if you have a large enough sample size, you will not really have a problem. The normality assumption will be okay. Okay, you don't need to be over concerned that it is not normal on this scale if you have a very large sample size to compensate. Okay, so take this data and I say if I've had so take this data and I just decide to do a simulation. I spend time checking how to simulate from this distribution, and I've done the simulation. I've shared that data set. I think it's on week 6 notes. I don't put on that data. So I've shared it both as SPSS so that if you're not using R, then you don't need to worry. So I've saved it both as SPSS and as an array data frame. Okay. So I say contain a sample of simulated responses using the path parameters in the model. The simulation returns multivariate normal samples. Okay. These have been recorded into Lekes K. So the simulation itself normally will give us normal sample, and I just recorded it myself to a Lekes K on the 7-point using my own cutoffs. Okay. So I said table 3 of Kim R shows the names of each of the variables. These are the names. I think I brought them here. Where are they? Are they in here? Okay, maybe not. But I think they are there in the notes. Okay, so it shows the name of the variables. And in here, these are these are just the labels like PP, Q05, PP. These I've used the same names in the simulation. Okay, I've used the same variable names in the simulation. Any questions there? So please read this manuscript, read this one to see the description of the items and so on, and what they did. What they actually did is that they were trying to do a confirmatory factor analysis by testing on a new set of data that they collected. Okay, so they collected a new set of data. This is a factor solution that has been proposed for a long time and is being used on this K. And then they obtain a new set of data, and then they try to reproduce it. So in here, this is basically, if you look at this model, you remember I said that we need to take from this model to our factor solution. So factor 1 has P05, P06, or P07, 24, 11, 4, and 25. So if you come here, that's the layout. Okay. So in our Lavan, this factor 1, those are the manifest variables for factor 1. For factor 2, those are the manifest variables. I might have missed out something. I think I pasted something different. Look, I didn't include a simulation here. Oh dear, I will check it. It will be in the listing. Yeah, I will show you the simulation. When I open the file, we'll see it. I think I copied the same thing twice. So what I want to show you is how you specify this one in the simulation. Okay. So basically, in the simulation, you will take these coefficients and put there. So I'll put 0.076. So if I want to simulate the data in here, I will put say I'll put 0.756 times that. I will do this for all of them. Okay, then I do the simulation. So I think I copy and pasted the same thing twice instead of I will show you what it does. Anyway, so model specification, that is what it is. And so the key thing is that because I have the structure here, I've put all the variables that go straight to this one within the same model, okay, within the same line. In the structure equation modeling, as we'll see later, I prefer to put each line on a separate, so I prefer to put, if F1 has 10 lines, I prefer to put 10 lines, but it is easier here to generate like this. Okay. So I'll go to the computer and then show you what to do there. So in here, the function to estimate that in Blue Sky, well, this into factor. So the function to estimate that in Blue Sky is a simulate data, which is I think from one of the Laban packages, but it's also a base program in R. Okay, so when I simulated it based on what I generated, this is what I found. So if you look at the nodes, you will find that my graphing programs are different from this one. I use the simplot. It does this, but it's so long that I can't see. You can't even see anything. So I just stopped using the sim plot. So basically my own gives something looking like this, which we're going to do together. So this is one form. This is another form of the same. So depending on how you want to see it, you can generate a path that looks like this or a path that looks like this. We'll go and do it together. And then I use a Lavant plot to do that. So first we feed the model and then we generate it. If we come here, you find our factor 6. So this one, I think they are standardized. Sorry, this one say unstandardized. Is that true? Standardized. I think yeah. So you'll find that there are two solutions. One is unstandardized and one is standardized. The unstandardized one is the one that we'll see from the output of the data. The standardized ones is if you want to report standardized coefficients. But in any case, you may get a graph that looks like that. Okay. For those who like path analysis, it may be easy to interpret. So let's go here. And here, what I just do is maybe let's start from here. When we generate the other one, we'll generate our own pictures. So basically, if you are using the SIM package, SEM, or the CFA in Lavant, then these are the output that you get. So you get your overall model feed. Okay, and remember that this model is a very good feed. So you can use it to immediately begin to say, what are these? Here you see a number of parameters that it says in the model, they're 190. But here degrees of freedom are actually 260 based on this model. So your sample size, anything around 190 may give you problem fitting the model, this particular model, based on this information here. But because your degrees of freedom are 260, okay, for this one, you also want to make sure that your sample size is beyond this to be sure that you are doing estimation. But the key thing is here. Your sample size, sample size around 190, you may get problems fitting the model. So the model may say, I cannot fit, I have negative variances and so on. If you want to fit this model, you want to feed this data to a sample size around 190. Okay, so that's the key thing to remember. And here, what do we find? The key thing about this result is I know that this is a very good fit. This is almost a perfect fit. So what chi-squared do we get? We get the chi-squared of, where is it? P-value is 0.74. Okay. And the standardized p-value, the standard for p-value is basically 1. So this, the p-value, telling that this is a perfect fit. Okay, it's a near perfect fit.
I have a question. Can you please explain what degrees of freedom means? Because I have difficulty to understand this. Like, what's indicated for degree of freedom? What is it?
Yeah. So in normal statistics, when we say your degrees of freedom, is like your degrees of, if I give a sample, let's suppose I want to find, if I want to find a sample mean, and I know that if I take different samples, I will get a different mean. So if I have, say, 10 people and I'm taking 5 people, and from those 5 people, each group of 5 people, I find the mean height, okay? For every group of 5 people that I find, the mean will be different. Now, I'm taking a sample of size 5, and I want to find the mean, okay? And I want to do a distribution of the mean. Then I say, okay, what's the degree of freedom for my test statistic? So that's where we come from. The degree of freedom for a test statistic says, we tell you how many data points, what's the minimum data point that you need, okay, in order to do the test. For the sample mean, the minimum data point that you will need, the degrees of freedom will be the sample size minus 1. Because if I know the total, if I know that the total is, say, 10, if I know 4 of the values, I will know the last one. If I know that, let me suppose I say that the total is 10. If I say the sum of 5 numbers is 10, and I give you the sum of 4 of the numbers, then already know the last number by subtracting from 10. Okay, by subtracting the total from 10. So the degree of freedom in that case, how many different values you can play around with. Okay, how many different values you can play around with in order to get to 10. I can change the first value, the second value, the third value, the fourth value. All of those I can change them because when I add them up, I can play around with 4 of the values. Let's put it that way. Sometimes I find explaining degrees of freedom very nicely with a cross tabulation. Let me just put one for you. I hope it doesn't take you out of what you were asking. So if I come in there and I say you like course, and you say yes, no, and say this one say pass course and then pass fail. So let's suppose we fix the number here and say I have 20 people, 25 people here, maybe 30 people here. Okay, that gives us a sample size of 55. So if I come here and say total, I know there are 55 people here. So first of all, the total here cannot be more than 55 because we're counting people. So let me suppose the total here was 40. Okay. Then automatically this number is fixed. It will just be equals to this number minus this one. Cannot be anything else. Because the total here must also be 55. You get that? So the degree of freedom that I have here is only 1. I can only change one of these. If I change this to 20, that will change. If I change this to 30, that will change. I cannot change 2 because the total must be 55. You see that? Okay. So the degree of freedom here is only 1. I can do exactly the same thing within the tables. So this total here can be 25. So I can put any number here less than 25. Say I put 20. Because this number must be 25, this number must be 25 minus 20. Okay, so it must be 5. Now, I can change this one to 15. That will automatically change. You see what I mean? I cannot change both of these because the total must be 25. I can do the same throughout this table. So automatically, this number, this sum here must be 30. So I can't do anything else because that's total. So I can say this minus this. Okay. And automatically, this again, I can use either this side or this side to find this one. So this number here, what would this number be? This number here, what would this number be? Nobody remember? The total must be what? 30? And 30. The total here must be 25. So it can only be 15, isn't it? It can only be 15. And that 15 satisfies both directions. This plus this is this plus this. So the table, if I change, so let me even do this one. Depending on which side you want, you can take this minus this, will be 15. It must also satisfy this total here. If it doesn't satisfy this total, there's a problem.
Right.
So if I come here and put 10, you'll see that everything will change. You see that? So my degree of freedom in this table is 1. If I can come here and put 20 or say 18, everything will change and the total will remain fixed. So in a 2x2 table, we say if you fix the marginals, you have only 1 degree of freedom. You have only one place that you can change to maintain the structure of the table. Okay. This concept takes for all your statistical tests. So if I fit a regression model, like I told you about fitting, if I have a sample size of say size 10, and I want to fit the regression model, from our statistical calculation, we know that you need to fit the constant and the slope. So I take those 2 parameters from my model and get 8 degrees of freedom. Okay, so for me to calculate the degrees of freedom here, I need to know the number of parameters in the model, which is this one, where is it? You see here, this number of parameters is 190. So my sample size must be more than 190. Okay, now, but these are just parameters that it's doing. In case there are other functions to be calculated, then they will all add up to this. Okay, something else. When we do testing, there are some statistics have 2 degrees of freedom. Chi-square has only 1. Okay, and it's also based on what else we're estimating in the data. So we estimated some variances, we estimated some covariances, and they all go to add up to the degrees of freedom for this table. Okay, but the most important thing is that the degrees of freedom is telling us how many data points we are free to choose. Okay, that's what it's written. How many data points we are free to choose their value and in order to do our estimation. I hope that makes some sense.
Okay, yes, thank you.
Yeah, but I find that this is always this. I find this to be easier for me to explain, but I don't know where it translates to the person I'm explaining to, where it makes sense in terms of degree of freedom. But basically, it's the number of parameters, the number of free points, the number of points that you can choose to maintain the model, not to change the model, to maintain the estimation as what they are.